Hello, my name's Isaac.
And my name is Aditya.
And together we are the 2020 to 2021 Ultrasound Guidance Team. Within the United States, over 200,000 people are diagnosed with kidney stones every year. PCNL is a common yet complex procedure that is used to remove large stones and involves the insertion of a long needle into the patient's back. Unfortunately, the high level of precision and spatial understanding required can lead to surgical complications like infections and hemorrhages.
Current PCNL procedures require the surgeon to hold an ultrasound probe with one hand and manipulate the needle with the other. This means that the needle has to be inserted into the target region at an angle, making it difficult to accurately reach the target point in the kidney. Our proposed solution is a device that uses a mirror to reflect the ultrasound image. The needle is aligned with the ultrasound image by passing the needle through the mirror. This way, the surgeon has a better spatial understanding of the ultrasound probe and the needle, and can visualize the target area and the needle insertion point much more accurately.
Our goal for the project was to create an attachment for an ultrasound probe that adds a needle mirror mechanism which can be easily rotated while keeping the needle aligned with the ultrasound image. We also developed a user interface that complements the device and provides users with real-time ultrasound images, useful telemetry about needle orientation, and a 3D visualization of data. A 2-to-1 rotation between the needle and mirror is needed for the needle to be in line with the reflected ultrasound image. Therefore, we implemented a belt drive system using timing belts and 3D printed belt wheels. To properly tension the belts, the center distance between belt wheels can be adjusted and 2 springs offer variable tensioning. We observed a baseline error of about 0.5% with 6% error at edge cases.
The user interface utilizes the Claris Ultrasound API to obtain real-time ultrasound images. The user is also provided with intuitive metrics about needle orientation and the ability to visualize a 3-dimensional view of the area being scanned. Using real-time ultrasound images and encoder readings, an image is plotted in a 3-dimensional space that helps visualize image rotation along the scanned area.
We also created a PCB that has a 0.7 degree resolution encoder and uses a serial connection to send readings to our user interface. Menu navigation allows the user to display the encoder readings, connect to Wi-Fi, and perform over-the-air firmware updates.
We used the Phantom to simulate tissue and test image rotation and image depth. To provide a medium for the ultrasound to pass through, we submerged the lower half of the device in water. The 6 diagonal dots and 4 vertical dots validate that our system can reflect ultrasound images with a mirror and that our system has a sufficient depth of penetration. Our tests also prove that we are able to visualize ultrasound images in a 3D space across a desired 40-degree range of motion. We also tested our device on a kidney phantom at UMass Memorial and were able to visualize the surface of the kidney. We believe our system has the potential to improve clinical outcomes and can also be adapted for a broader range of ultrasound-guided needle intervention procedures.